Hello, George Romanic here. Today we have a very special problem, in particular if you are a student of atmospheric sciences or oceanography. In today's video we have to demonstrate that the horizontal component of Coriolis force will result in a motion that is a circle. Namely, in the absence of all other forces except for the Coriolis force, an air parcel will go forever in a circle, and that circle is called inertial circle. We already derived this in a separate video, but there I use natural coordinate system. And now you can see the text of today's problem on your screens. And you see that the text says that we have to start from Navier-Stokes equations in a Cartesian coordinate system. So, Navier-Stokes equations in Cartesian coordinate system are in the zonal direction. So acceleration du dt is equal negative 1 over rho delta p delta x plus fv and plus nu nabla square u. And in the meridional direction, namely south to north, dv dt is equal negative 1 over rho delta p delta y minus f times u plus nu nabla squared v. And we don't need to write third momentum equation because we are only interested in horizontal motion. Now we assume there are no other forces except for the Coriolis force. So viscosity disappears, so it's an inviscid fluid, and the pressure gradient force also disappears. Now some of you might say, how is it possible to have motion if we don't have pressure gradient force? It is, in principle, you can say pressure gradient force initiated the motion, and then for some reason there was no more pressure gradients, and hence there was no more pressure gradient force, but due to inertia, an air parcel or water parcel continues to coast. In that case, we still have Coriolis force. So you can see that now our momentum equations only have Coriolis force terms. And basically what we need to do is solve this system of differential equations. When we solve this system, you will see at the end that the solution will give us a circle, namely circular motion. So how do we solve this system? Well, one way to do it is to differentiate this equation with respect to time and then combine with this with the first equation. So if I differentiate this equation with respect to time, I will get that d second v dt squared is equal negative f du dt, where f, you should know by now that f is Coriolis parameter 2 omega sine phi, where omega is angular velocity of our planet and phi is latitude. So now we have this equation. This du dt we can take from this equation over here, and notice that I will have that d second v dt squared is equal negative f du dt is f times v. So this becomes, the right hand side becomes negative f squared times v. And consequently, this equation, if I move this to the left side, will become d second v dt squared. When I move this to the other side, it will be plus f squared times v equal to 0. And this is a second order differential equation, and it is a homogeneous differential equation. There is nothing on the right hand side, and this is very simple to solve. Now in this video I will not go into mathematical details of solving second order homogeneous differential equations, In principle, I will just tell you this. In principle, function that satisfies this equation would be v as a function of t, because we have derivative with respect to time, is equal some constant that can be complex, e to, let's say, kt. This function, if you plug in over here, will satisfy this equation. So if we do that, we will get so-called characteristic equation for this differential equation will be this one, k squared plus f squared equals 0. So you can see I skipped some steps over here, and these are some steps that I will explain in some of the future videos in more details. But basically, if you plug in this over here, you will get this equation over here. And this is an algebraic equation. This is differential equation. And this algebraic equation is called characteristic equation of this differential equation. Now we solve this algebraic equation. You can see that k squared is equal to negative f squared. Or we will have two solutions. Solution number one, k1, is equal I times f. And solution number two, k2, will be negative I times f. Now, of course, you need to know, that goes without saying, that I is square root of negative 1. Imaginary unit. So now when we have roots of this characteristic equation, we can see that this root is a complex number, and we write this k in the most general way as a complex number, which would be alpha plus minus I beta. So plus minus corresponds to two different solutions. And you can see that in our case, alpha is equal 0, because we only have imaginary part of this number, and beta is equal plus minus f. Okay. So now when we know that, then you have to know another principle of mathematics, that if the roots of these characteristic equations are complex numbers, then the general solution has the form that v of t is equal e to lambda t, some constant c1, cosine f, well, I should not write f right away. Cosine beta t plus I, some constant c2, times sine of beta t. And notice that our beta is f and our alpha is 0. Because alpha is 0, this term is 1. And we get that solution v of t is equal c1 cosine ft plus I c2 sine ft. So as you can see, this is a little bit more advanced video. You have to know how to solve differential equations. In this video, I'm not going into very great details on mathematics of this. I assume you know that. If you don't know that, then you should go back and watch some videos about differential equations, namely how to solve second-order differential equation. I assume you have some basic knowledge of that over here. I mean, when you are watching this video. So now we get with this general solution, but we have two constants, c1 and c2, that are unknowns. However, the problem, as you saw on your screens, gave us initial conditions. And the initial conditions are that at time t equals 0, u component is equal u naught, and v component of the wind is equal v naught, some numbers. These are fixed numbers. For example, this is 5, this is 7 meters per second, who knows. So we know this. These are called initial conditions. And we can use these initial conditions over here to find these constants. So for example, at time t equals 0, so when time is 0, v is v0 is equal c1, cosine of 0 is 1, and sine of 0 is 0. So I will get c1 plus 0. And I can see right away that constant c1 is v naught. So I can write that v of t is equal v naught cosine ft plus I c2 sine ft. This constant c2 will be determined from the second equation. And second equation is equation for u. Here we have equation for v, but we have two velocity components. We have u and v velocity components. So now to find u component of wind, I can go into this equation. And from this equation, notice that u as a function of t is equal negative 1 over f dv dt. And now, if I differentiate this equation with respect to time and plug in over there, I will get that this is negative 1 over f dv dt. So derivative of cosine is negative sine, so I will have negative v naught f sine of ft. Derivative of sine is cosine, so I will have plus I c2 f cosine ft. Notice that this f and this f cancels, and this is then further equal. So this is further equal. Can you see from me? I hope you can see from my back. This I will put cosine term first, so it will be negative I c2 cosine ft. This minus and this minus will give me plus v naught sine ft, and this is of course u of t. Now I can again use these initial conditions to find this constant over here. So at time t equals 0, u of t is u naught, and that is equal negative I c2. Cosine of 0 is 1, so that would be 1, and sine of 0 is 0. So you see that this negative I c2 is v naught. And now finally I can write these two equations, my solution, without any integration constant, and I will write it over here. So you see that u of t will be negative IC2 is u naught. U naught cosine ft plus v naught sine ft. And v component of the wind, namely v of t, will be v naught cosine ft minus, because IC2 would be negative U naught sine Ft. And this is our solution. Now, if you are very good at mathematics, you can see that this solution immediately gives you an equation for a circle. If you are not very proficient at mathematics, you will look at this and say, rah, 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 I don't see any circular motion over here. But don't panic. I will demonstrate to you that indeed these two equations, when combined, give you an equation for a circle. To do that, I have to erase this part over here. Okay, so the blackboard is clean now. Before I demonstrate that this is equation of a circle, you have to know what is a general equation for a circle. And that equation would be that some x squared plus y squared is equal r squared, where r is radius of the circle. This is equation for a circle. And I even demonstrated that in my video on cylindrical coordinate system, if you want to check that. Now let me show you why this is equation of a circle. If you have a circle, and here is the center of the circle, and let's say this over here is radius r. Now, if I take this to be my x-axis, and this to be my y-axis, then this radius r will have this component in the x direction, and will have this much in the y direction. And you can see from Pythagoras' theorem that this squared plus this squared will give me r squared. Now, if this radius is, if I am moving this radius around the circle, I can go anywhere. I can go here, for example. This equation still holds, because if I project, this equation still holds. If I project this to xy plane, you can see I will have this much of x, which is, by the way, negative now, the way I position my x-axis, and I will have this much y, which is also negative, because it is going in the negative y direction, but it doesn't matter that they are negative, because when I square them, again by Pythagoras' theorem, I will get radius of the circle r. So this is a demonstration that this is equation of a circle. So what we need to do now, we need to massage these two equations to demonstrate that we will get something like this. Now to do that, I will square first equation, and I will square second equation, and then I will add them together. So let's do that over here. So first equation squared will give me u squared. I will omit u squared of t for shortness. So u squared plus v squared equals, that's the left-hand sides of these two equations, u naught squared cosine squared ft plus u naught v naught 2 u naught v naught cosine ft sine ft, and plus v naught squared sine squared ft. So I squared this equation over here. Now I need to square this one and add to this. So plus, I squared right-hand side of the v equation. I will get v naught squared cosine squared ft minus 2 u naught v naught cosine ft sine ft and plus u naught squared sine squared ft. Now I hope you are not a beacon and you can see right away that these two terms cancel. They are the same up to a sine. And now what you need to know, and if there is equation that you should memorize in your life, that should be equation that cosine squared of some angle alpha plus sine squared of some generic angle alpha is equal to 1. This is one of the most important equations in human history, so you should know this equation. Now, if you know this trigonometric identity, then notice if I factor u naught, that I will have cosine square ft plus sine square ft, but thanks to this equation that will be 1. So this and this together will give me just u naught squared. Similarly, if I combine this term and this term, I will just get v naught squared because cosine squared ft plus sine squared ft will give me 1. So with that in mind, we can write that u, let's now put as a function of time, squared plus v as a function of time squared, namely this, is equal a constant, u naught squared plus v naught squared. But this is a number, some constant, because this comes from our initial conditions. And this is demonstration that Coriolis force, because this equation looks exactly like this equation, I could assign this I could call this r squared, doesn't matter, and I get the same form. And you can see that Coriolis force results in circular motion of an air parcel if there are no other forces affecting. And I purposely left Navier-Stokes equations here to remind you that we neglect viscosity, we neglect pressure gradient forces in the horizontal direction. So let me maybe just say a few more things about this. If we take our initial condition over there, then the initial condition will look, let's say, this is u naught at time t equal 0, and let's say this is v naught at time t equals 0. These are components of the wind, which means resultant wind, let's call it capital V, would be like this. Now, what this equation is telling us, that these components u and v will change over time, but when I square them, I will always get this wind v naught. So that means, let's say, well, this was at time t equals 0. Let's say at time t equal t1. We have wind vector that looks like this, okay? So this would be wind vector v capital of t at time t1, sorry. So what would be components in this case? Well, component, I would have this to be my v component and this to be my u component. Clearly, this u, well, this u is similar to u naught, but this v is definitely not the same as v naught. They have opposite sense. But when I square this one, these two, and I square these two, I get the same v of t. In other words, if I have an air parcel, now this was air parcel over here having vector like so, v of t naught, like this. And now in time t1, this parcel of air has this velocity. That means trajectory will go like that. And this trajectory to me looks like a circle. And this circle is called inertial circle. Again, I described this whole thing in another video called Inertial Oscillations. Now you should not make a mistake to think, of course, that the radius of this circle, I'll call capital R, radius of this circle is called radius of inertial circle, and that's of course not this. This is now this is dimension of space. Another important thing about this video, I believe, is to demonstrate to you how important it is to use the right coordinate system. When we used natural coordinate system, we derived this solution in 7 minutes. When we use Cartesian coordinate system and Navier-Stokes equations in the Cartesian coordinate system, I don't know how long this video is, 20 minutes. It took us maybe more than 20 minutes to come to the same conclusion that we obtained using better suited coordinate system for this problem. And in addition to getting additional knowledge on Coriolis force, I hope this video highlighted the importance of coordinate system choice. At the end of the day, physics is the same, as you can see. But the way to get to these results depends on your choice of coordinate system. You can make your life easy or difficult depending on the reference frame and coordinate system that you're using. Until next video, goodbye.